All right. Good afternoon, everybody. Thank you for joining us for another Grease Thief Thursday today. Today, we will be talking about rheology, understand and measuring the flow behavior of grease. So, first, we'll start off talking a little bit of rheology versus die extrusion. So, in the chat, I will link the video that we have previously did on die extrusion. If you have not seen that, you can go back and check that out. But rheology is an advanced test that requires a technician with advanced skill to prepare, run, and then analyze the testing results and associated costs for that high value data gathered. Die extrusion is standardized in D7918, and it's able to be run by more technicians and requires less training to run the testing. And it's also going to be a much quicker test. So rheology for a sample is going to take about an hour to run the tests, and then there will be the analysis time to interpret the results. For die extrusion, you're going to get those results and be able to interpret them in just a few minutes. Rheometry is performed on grease samples to understand the deformation also that occurs under shear stress. So for rheology, the testing is going to give us insight into our in-service grease performance and the deterioration that's happened while it's been in service. So that's obviously very important to monitor to ensure that we're operating our assets as reliable and safely as possible. So during the presentation, we'll talk about some different values or data that we're going to get. So we'll review that real quick so everybody understands. So one thing you'll hear us talk about is G prime. And G prime is going to be related to the grease's ability to stay in place. So it's kind of that thickness, how thick is that grease. Oscillation stress, or the yield stress, also called, is related to the shear behavior of the grease and oil separation. So that's going to give us some insight into that behavior. And then we have the recoverable compliance, which demonstrates a grease's ability to recover and spatially restore from a force. So it's imagining the rollers coming through, coming across the grease, and then as that roller passes, the grease kind of recoiling or recovering back into place and getting ready to do it again for the next roller. So this is obviously a very important data to understand because grease is a viscoelastic material whose ability to recover from forces and how it responds to shear stresses will change over time while the grease is in service. So monitoring that change is important to understand when we need to take action to prevent any undue, wear or any kind of issues like that with our asset. So when do we want to run rheology? So one time that we're going to recommend it from the laboratory is if we see a dynamic change in the flow behavior when we're running the die extrusion test in ASTM D7918. So as we talked about in the beginning, die extrusion is a quick test. It can be used as a screening test for candidates for rheology testing. If the die extrusion looks good, we don't need to perform rheology, but if die extrusion is leading us to believe that there's been some kind of change in the grease's properties, running rheometer is going to allow us to understand those changes and then quantify it as well with data compared to that baseline. Rheology also is helpful for low sample volume. If the customer wants consistency data, but they don't have a lot of sample, the standard D7918, it does outline how much grease is necessary to get a full die extrusion run. Sometimes you don't have enough grease to do that appropriately or per the standard, but there's plenty enough grease to do that advanced consistency testing. So it's a lower volume required for the testing. And then we also use rheology in our compatibility testings so we can evaluate mixtures of greases and how they performed after they've been run in the test stand. And that's helpful, again, to evaluate those changes in grease And if we see a very negative change, we're able to show that to the customer, and they're able to avoid mixing those greases and avoid that incompatibility happening in their asset during operation. Some of the background on our rheology method at MRG. So we've modeled the work, modeled this on work completed by Brian Johnson. The paper is titled "The Use of Stress Rheometer in Lieu of Cone Penetration." So it's modified from DIN method 51810. And we use that to study in-service greases for MOVs and wind turbines. The method uses a 1 degree cone. It's a little bit challenging to see, but if you look in that image there on the right, on the top of the geometry, you'll see a 1 degree. And that's talking about the geometry almost looks flat, but it is at a 1 degree cone. And then, as I mentioned before, samples are run on the oscillation stress and the time creep profile. The yield stress gives us the oscillation stress and the G prime values, and the time creep profile gives us the recoverable compliance of the grease. So we'll talk a little bit more about each of the results that we get from the testing. So as we said earlier, G prime is a measure of the structure of the grease or its dynamic rigidity. It's related to the grease's ability to stay in place. Obviously, you think about that with NLGI grades. The higher the NLGI grade, the more likely that grease is going to be to stay in place. Whereas the lower the grade, it's going to be able to be a little bit more movement in that grease's body. So we have a lower G prime value would be indicative of a grease that's gotten thinner while in service. And if we get a higher G prime value, it indicates a grease that's thicker than its original baseline. And every once in a while during our analysis, we'll see differences in die extrusion and G prime. And this could indicate that the grease may not behave as expected with regard to shear response and flow. And then this could result in inadequate lubrication film formation inside of our asset. And for this one, the units reported are in pascals. Next, we'll talk about the oscillation stress or the yield stress. This corresponds to the transition point from elastic to plastic deformation of our grease. So it's related to the shear behavior of the grease and oil separation. So if we had a lower oscillation stress, potentially indicate that the oil in the grease may tend to separate more readily from the thickener, or obviously that the grease would yield more and could leak out of the bearing. And if we had a higher oscillation stress, it could lead to decreased pumpability, and this could indicate that on startup, it may require a higher starting torque to get everything going. This one is also reported in the same units of pascals. And then the third data point that we get from this testing is our recoverable compliance. So this is used to evaluate the grease's deformation under a steady stress and recovery. So the grease gets stressed, and then it sees how it recovers after that stress event. This is related to a grease's ability to recover and spatially restore from a force exerted on the grease. The higher the percentage of recovery, the more effectively the grease recovers from a force that's exerted on it. The lower the recoverable compliance, that could indicate that the grease will tunnel or migrate from the lubricating path. So kind of as it's pushed out, it won't recoil back in. It'll kind of just continue to get pushed out. And the units of this is a percentage. So it's just a percent recovery compared to the baseline. So during our evaluation process, as we mentioned a little bit when we were talking, the sample or the in-service sample is going to be compared to a reference baseline grease to see how it's changed while in service. This is obviously very helpful to understand how that grease has changed if we're getting very similar responses from the in-service sample and the baseline. We know that that grease is going to be performing very similar to the fresh baseline that's being added, or the new grease that's being added each time. And And then the evaluation is done using the instrument software, and I'll have some examples to follow later on in the presentation so you can see what that looks like. So we mentioned the compatibility testing, and rheology is an extremely important part of the evaluation for the compatibility testing that we do. This is also very important right now with supply chain issues with lubricants, that we've had a lot of customers that they can't get a grease and they need to find a compatible grease that they can use instead of having to worry about, if we put this in, are we going to have a problem with the asset that we're maintaining. So in that compatibility testing, we follow ASTM D6185, and that outlines the primary testing that the grease mixture should pass. And once the primary testing is satisfactory, we move on to an additional secondary testing that we perform. So in the secondary testing that we perform at MRG, we get the binary mixtures as laid out in the standard of 50-50, 10-90, and 90-10. And then we mix those or work those greases and the reference baselines in the test stand you see there on the right. It's got some small bearings. They run for 72 hours to achieve a little over 18 million mixing events. So plenty happening in those 72 hours for us to be able to evaluate the change. And once the runtime is up, we sample per D7718 to get the representative sample from our bearings. And then the aforementioned testing that we just talked about, we will evaluate those mixtures and we'll see, have they changed as expected, or is there an unexpected change? Has the grease gotten very soft, very hard, what have you, in the testing results? So this would be helpful, as I mentioned, in the potential future issues that mixing the two greases might have. Sometimes you find that, you know, the 50-50 might be okay, but the 10-90 and 90-10 are not satisfactory, and you find that you'll have problems right at the beginning when you're introducing one grease, and at the end when you're almost on to the new grease fully. So it's important to kind of look at all those mixtures to have the full picture and understand, is there going to be a negative impact mixing these two greases together. So first, we're going to go over the oscillation stress profile results. So here we have two different profiles. They look very similar. One thing that I'll point out is that on the y-axis on the left, where the G prime is, you'll notice that that scale is different in the two images. So the image on the right, even though they look the same, has a much larger G prime response. It's over 120,000, whereas the graph on the left has a G prime response of 21,500. So that would be important if these are from the, comparing to the same baseline. One has changed drastically, or maybe they both have, and the baseline's in the middle. But just wanted to point that out with the graphs, that even though they look the same or very similar, that they have different responses as far as the G prime or the thickness of that grease. Here we have the time creep profile results. So we have two different recoveries shown here. So on the left, I think that this one was about 8% recovery, but we can see that the grease recovered a little bit, and the grease on the right had about a 25% recovery. So just kind of showing the difference in what that looks like. Again, samples are compared to their baseline, so there is no right or wrong answer as far as the recovery compliance goes for the baseline, but we'll compare the in-service grease to the baseline, and we want to make sure that that's what we're comparing to understand how that grease has changed. Next, I will go to the chat and we'll see if there are any questions that came up in the conversation. currently not seeing any questions in the chat, but I would like to appreciate or say thank you to everybody, and I appreciate you taking the time today to stop in and check out our live stream webinar and learn a little bit about grease rheology and how we can use that to evaluate grease and as it's changing in service.